First, I want to thank you, everybody, for coming. This is the ArcGIS API for Python for analysts and data scientists. I'm Andrew. This is Young Yao, and Rohit's going to be along a little later at the end of the session. He's being held up at the moment. And if you want to follow us on Twitter, take pictures, pester us, add us, follow us. Those are our Twitter handles. So we're going to start with the introduction, and we're going to talk about sort of this issue that's out there. And you have analysts and developers and programmers, and they all cover various aspects of workflows and things like that. And an analyst gets paid for doing insights, and the data developer gets paid, to use to code that produces the insights that the analyst uses, and then the programmer actually just does code. And above that line that's up there, you see some of the languages or products that they might be using to do it. But you can also use Python across the board to do all this. And the Python API helps you do some of these tasks. And this is just an interesting slide, and this is a data science course. I believe it's at, of course I'm on stage, and UC Berkeley. And they've been offering this course, and it's literally standing room only in their courses to talk about doing data science with Python. And that's how popular it's going. And in recent years, over time, the usage of Python has grown so much that it's supplanted R as a language of choice for data scientists. So we're going to go ahead and start talking about analysis, and we're going to look at the Python API. But the first thing we need to look at is what is the ArcGIS API for Python? And it's a collection of tools and classes that you can use to work with your WebGIS. It's very robust and friendly, and it has the same look and feel across the whole board. It's broken and modularized into little pieces. So you have your Geo Enrichment, and you can work with your geometry. You can also leverage geoprocessing tools, so hosted public geoprocessing tools. These are tools that people put on the internet that you can leverage their servers to do your analysis. We have Geo Analytics for big data. We have spatially enabled DataFrames, which are really powerful and can work with your data. You can hit Raster Analytics, and you can even do deep dives into your information by doing deep learning using the new ArcGIS Learn module. And the other thing is it works integrated really well with Jupyter notebooks. So ArcGIS plus Jupyter equals love. You're going to love your data when you do this, and you're going to be able to take this information and create robust, reproducible workflows and put them on Jupyter notebooks. But where does it all start? And it starts with your GIS. So you do from arcgis.gis, and you import GIS class. You can instantiate it many different ways. You can connect to online or your enterprise. So we do GIS, and we're passing the URL to our organization, and we're handing it our credentials, in this case, username and password for both of them. Then the one below it, we're connecting to our enterprise, which is a portal, so your on-premise enterprise. So this just isn't limited to online. You can do it with your local enterprise portal. You can search for content very easy. Off the GIS object, there's the concept of managers. So you can do GIS content, and you can do a search. And you can bring up all content that exists within your organization by default by itself, or you can go out and see what other individuals have shared to you across the whole platform. In Jupyter Notebooks, it provides a rich HTML display for each item, and they're interactive as well. So if you were to click on the blue text there, it would actually take you to the URL endpoint where that item exists, on whether if it's your enterprise or just online. Then you can also visualize data, which is very important. Before you can make insights, visualization is also very important. Just to know what your data looks like, sometimes can give you insights of how you're going to go about and start looking at and approaching your information. So we have a built-in map widget, and we take our GIS object and you just do gis.map, and then you type in the object again, and you get a rich display powered by the ArcGIS JavaScript on the back end. You can add layers, both feature layers and spatially enabled data frames. But let's get into some more soup and nuts things. So let's look at spatial analysis and how we can discover relationships and patterns and trends within our data. And this all starts with the ArcGIS.features submodule. And it gives you a set of spatial analytic tools that you can start doing information. You can summarize data, find locations, And you can do proximity analysis and manage your data sets. So if we wanted to go ahead and summarize data that we have on there, we can access our feature layers in this case, and we can run and aggregate points in there to collect information. And then we can use that rich displaying module to show the points and intensity of those points at the given locations. We can enrich information, so we have a whole submodule that deals with Geo Enrichment, but this is a simplified cut-down tool. If you don't want to dig into everything, you can leverage this analytics tool and enrich an individual layer. So you just do enrich data.enrich layer, and it gets back your information, and you can get it back as a spatially enabled data frame from your feature set and display the results. If you want to figure out what's near what, you can do proximity analysis. You can pass in your planned routes, and it'll optimize them, return back that feature layer, and display it on the maps, given the points that you have. Additionally, you can also create buffers. So if you compare this to ArcPy, some of that functionality that you're seeing there, you can start buffering information, and you get the same feel, but instead of being powered locally, you're being powered by your WebGIS. This happens by doing from ArcGIS.features.use proximity. So you go into that module, and we're going to import the create buffers. We're then going to pass the information in, so the location of our fire stations, and we're going to create our buffers on 4 miles, and then persist that information out to our organization as a layer. We can also do overlay analysis as well, so we can overlay our layers. So if you have more than one layer, you can overlay it and determine critical infrastructure within risk boundaries, as an example. And we can analyze patterns, so we can identify, quantify, and visualize the spatial patterns of interest with our data. In the Analyze Patterns module, you can interpolate points and create constant surfaces. So if you have rain data, in this case, you can create a continuous surface with the information that's in there. Moving away from the features submodule, we can look at geocoding. And geocoding allows you to geocode single points or multiple points, or even do reverse geocoding. So it's in the ArcGIS.geocoding module. Geocoding is pretty powerful, so it allows you to find where stuff is from descriptive information. So we're going to geocode by single line and by multi-line. You can either pass in a dictionary broken into its common parts, like address, city, region, and postal, or you can just pass in an address, like you see on the right, with the single line geocoder. And it returns back a feature set, and then you can draw that on a map or use it for additional analysis down the road. You can look for points of interest. So if you know the extent or the area you want to look, in this case, I'm interested in Starbucks, and I give my extent around Union Square, pass it in, and I can get all the locations so I can get my caffeine fix. We can also do batch geocoding, and that's passing in a list of addresses. So you can use any array-like objects, so tuple, list, or even an array, pass that into the batch geocoding tool and get your results back. We can reverse geocode locations, so if you know the lat long of your location or the XY, you can pass that in. And you can even specify it by location code. So if you're French in this case, you can get it back, the results back in French. Or if you're English, you could say I wanted an EN and get the results back in English instead. We allow for a rich network analysis, so it's basically figuring out it's that what's near what kind of answer and question. So we can do network analysts, and we can look at different capabilities. We can do simple routing, optimized routing. You can do the service area, where you can specify your distance you can travel with a given amount of time. You can do location analytics, find closest facilities, so it's very robust. Basically what you can do on desktop, you can use the WebGIS to do your network analyst functionality. To do a service area, it's pretty straightforward. So we access our service layer, and once we have that, we can start building out what we have. We're going to do solve service area and pass in our feature set points. In this case, it's fire stations. We want to know how far you can travel in 5, 10, and 15-minute intervals. And we can build that out and show the coverage to see if we need to build either maybe a new fire station or optimize something so it works better. The ArcGIS.Geo Enrichment module is If the under analysis, when we looked at an enriched layer, that's just a simple one. This is Geo Enrichment on steroids. You can dig down into the nitty-gritty of things and really produce very dynamic information. You can get facts about your area, and you can do it from a street address, points, lines, or polygons. And you can generate reports off this, charts, and even get it back as pandas DataFrames, spatially enabled DataFrames as well. You can use it to create reports, and these reports are fully customizable, and that's done by using the create report function in the ArcGIS.GeoEnrichment submodule. These reports can be fully customized if need be. You can replace the logo, like Esri, with your own logo, and completely make them to fit your organization's need for need-be usage. Next, we can also dive into Geo Analytics, and this is basically getting into large vector data sets, tabular data, and even raster data sets, and it's in the ArcGIS.GeoAnalytics model. And the GeoAnalytics tools are quite robust. We have summarized data, we can manage data, so getting data in and out of the big data store. You can do proximity and finding locations, and we can even analyze patterns. We can look at a demo of doing this. We're going to look at some Houston crime pattern analysis. So what we'll do is we're going to hook into our big data store in the first thing. So we're going to do ArcGIS.GeoAnalytics, get our data store. And we're going to add our big data store, in this case, from a network shared drive. From there, we can then take the information that we find and pull it in. And it'll automatically register our big data store, in this case, our Houston crimes by years. And we can look at the individual layers that are inside of there. We can then invoke batch GeoAnalytics on each one of them and start developing analytics. In this case, we want to take advantage of some hotspot analysis to find where crime patterns are occurring over time. So we're going to use a for loop and go over our whole category for them and do hotspot in each layer. We can then visualize and interpret those areas quite easily by leveraging the gis.map and adding our results to them. And you can see the different patterns. For example, burglary hotspots in 2016 versus auto thefts on the right in 2016. You can even take that further, and if you have data that's time enabled, you can add that to individual maps and look at them as well. So next, Young Yao is going to talk about raster analysis and continue on.
Cool.
Yep. Yeah, turn it on.
Cool. Thanks, Andrew. So let's switch gear and talk about raster analysis. I'm going to switch over to a notebook and give you a demo from there. Can you see the screen? Okay, cool. So first of all, I'm going to talk about some basics about raster visualization. So to start with, let's just, this is just standard code. Let's import the libraries and make a connection to your GIS, which can be the ArcGIS Online or your enterprise system. And then let's search for an imagery layer. In my case, I'm searching for this multispectral Landsat data. And let's say I'd like to use this first item, multispectral Landsat 8 data, which is the latest. So at this point, this is still an item. Let's convert this into your layer. And then if you query the layer by itself, you will get a screenshot for you to quickly look at how it looks. So in this case, I'm getting a Landsat 8 image at a global scale. So now we have the imagery layer. Let's add it onto your map. So first, let's create a map using this GIS map and have it centered at Redlands. And then use this add layer function to add a layer onto the map. And now we got the map added on this map widget. And we can zoom in and zoom out, so this is like fully interactive. So this shows how easy it is to visualize your raster data with Python API. And now let's talk about the raster functions. So raster functions might seem a little bit mysterious to you at the beginning, but they're essentially just algorithms you like to apply to your raster data. And there are two types of raster functions. The first type of raster function is the functions that you published with your data. In other words, when you publish your data, you can choose to bundle a few algorithms with it. And let's take a look at what this Landsat layer has. So all you need to do is just do properties and then raster function infos, and this will print out all of the raster functions that are associated with this Landsat layer. For example, as you can see here, we have one for agriculture, one for bathymetric, one for color infrared, etc. And let's say I'd like to apply this color infrared raster function to my Landsat layer. What can I do? So let's first import the apply method and just pass in this Landsat layer and then the raster function names, and then add the result onto your map. And this is what you'll get, a color infrared image, which is commonly used to highlight the difference between vegetation and other types of objects. And it's worth noting that at this point, this color infrared raster function is only applied to the screen extent, which means whenever you change the extent of the map widget, the raster functions will be dynamically applied to those uncovered area. And if you just move it to the left, it will be covered as well. So in that sense, it saves you a lot of unnecessary computation, and it's super performant in that sense. The second type of raster functions is the built-in functions in Python API. For example, if you just want to create an NDVI image, you don't need a raster function associated with imagery layer. You can just call this NDVI method. All you need to do is to import NDVI method and then pass in the layer, tell the method this is band 5 and band 4 near infrared and red band, and then add layer onto the map. And this is the NDVI image you'll get, and it's fully interactive as well. So you can also chain multiple raster functions together and make your analysis more powerful. For example, in the NDVI image over here, it's still kind of hard to tell which area has the highest NDVI. So let's just reclassify this NDVI map using the remap function over here, this inner function. So basically what this function does is to reclassify those pixels whose values are above 0.3, the threshold, to 1, and then the rest of the data to no data. And then we call this color map raster function to display those high NDVI area with green color. And then we add it onto a map, and this is what we've got. So those high NDVI area has become definitely more visible and obvious in this case. And also, when you are chaining multiple raster functions, you can use this draw graph method to kind of visualize your workflow. For example, here I started with the original Landsat data and then computed NDVI and then did remap and color map. So this helps you sort of verify and present your workflow, and it becomes more powerful when you are doing a presentation like this. And now you're done with your analysis. You can save your result as a new imagery layer that you can share with your colleague, or you can continue your analysis from there. Okay. Let me see. Is it okay if I can see that? Okay, so let's switch gear again and talk about deep learning. So this ArcGIS.learn module is a new module in Python API, which provides an end-to-end workflow with ArcGIS. And I'm going to talk about this module using a use case that we recently developed. So the goal is to detect all of the swimming pools in Redlands using deep learning. And we have two input data. The first input data is the high-resolution color infrared nape imagery, and the second input data is a nape file, is a shapefile that contains all of the bounding box of swimming pools in some sample regions in Redlands. So this use case has been presented at UC last year, and we have simplified the workflow a lot by using Python API. So let me switch over to a notebook and give you a demo from there. So the first step is to export training data for deep learning. In Python API, we have added a new method called export training data method. Basically, what this method does is two things. One is to divide the input raster data, in our case, the nape imagery, into sub-images, and we call them training chips. And then the second thing it does is to generate a label file for each chip that contains the bounding box information. And the size of each chip is specified by this tile size parameter. So in this example here, I'm dividing this big nape imagery into 9 training chips. But in practice, you can generate thousands or even millions of chips using this method. So now we have the training chips. Let's load the data into memory using this prepare data method and divide them into batches. So once your data is in the memory, you can choose to just show a few random chips to get a sense of how the data looks like by calling this show batch method. For example, here in the first batch, there's no swimming pool. And in the chip below, there are 2, and there are 2 here as well. So now we are ready to load a deep learning model architecture. So in this case, we are using a model called single-shot detector, which is one of the most well-recognized object detection algorithm in deep learning. And we have single-shot detector architecture as well as a pre-trained model has been predefined in ArcGIS.learn, so you don't have to define it by yourself. All you need to do is just do this single line, and it will be loaded. So before we start training, we need to find a good learning rate, which is probably one of the most important hyperparameters when training a deep learning model. And this LR find learning rate finder method gives you a learning curve to help you find a good value. So normally what you would do is to choose a value where the loss starts to go down very quickly. And in this case, the value 0.001 is probably a good value here because it's going down very quickly. So now we have chosen a good learning rate, we can start training the model. Let's train the model for 10 epochs. As you can see, both the training nodes and the validation nodes are going down as you train more epochs, which is a good sign. And the reason we are using a slice over here is because we want to apply those smaller learning rates to the first few layers of the neural network, and bigger learning rates for the later for the last few layers in the neural network, which is exactly the idea of transfer learning. So now we have a model. Let's detect swimming pools in our validation set. All you need to do is just to call this show results method, and it will give you a few random chips in the validation set. And the left side is the ground truth, and the right side is the prediction. As you can see, for the first chip, because there's no there's no swimming pool, and there's no here. And for the second one, as you can see, the ground truth is actually missing a swimming pool, missing 2 swimming pools. And our prediction actually caught that, so it's pretty good. And for this example over here, we are actually missing a swimming pool from here, so we are not doing as well. So overall, I think we have got some reasonable results. So now let's save the result and give it a name as a deep learning package. So if you are happy with your deep learning model, you can deploy the model as a web service, just simply by uploading the deep learning package as an item to the enterprise portal using this kind of method. And you will get some deep learning item like this here. So now we have deployed the model, we can do model inference with the package by applying the model to a new image using this detect object method. Well, you can just pass in a new imagery layer, and you will get the object detection and model inference results as a new imagery layer. So our result here is called pool detection full red lens. And here, let's create a map and then add this layer onto a new map. and we'll visualize the object detection results over here interactively. So these yellow squares are just swimming pool. So as you might have noticed, we are following a very like a similar pattern to those well-known machine learning libraries like scikit-learn. So basically, you follow 3 steps. You load the data first, and then fit a model, and then use the model to make prediction. So as long as you're familiar with those popular machine learning libraries, you can easily pick this up. And more features like image segmentation and classification are coming soon. So that covers all about deep learning and raster analysis, and I'll hand it back to Andrew.
Thanks, Yang-Yao. That was really cool. Can you hit number 6, please? All right, so now we're going to transition onto a data structure that we have available on the Python API for ArcGIS, and that's spatially enabled data frames. And spatially enabled data frames, what it is it's a pandas data frame where we've enhanced it to add very specific namespaces. If you think of it like a feature class, the feature class label would be on the spatial namespace. And then on the geometry column, you have a specific namespace that does geometry options called geom, G-E-O-M. And it allows you to do a lot of really interesting things and a lot of fun things. It gives you the ability to easy update query and sort of play with your vector data that you have. You can, so it's also built to do work. I just want to make this point, is that it's very interoperable, so it works with a lot of OGC formats like GeoJSON, and it also works with Esri geometries. You can consume multiple data sources, so feature layers, local feature classes, CSV files, and even other data frames. Some of the benefits is that you can put a lot of, it's very, when you load data, it tries to be very conscious of how it handles memory on your system to not slow it down or make it crash. You have on-the-fly spatial indexing. Like I said before, you can consume multiple data sets, and it tends to have a little small footprint with big results. And we started building it and modifying it using the .23 version of pandas. And we chose to use the accessor pattern because we didn't want to overwrite any of pandas' default functionality. For example, if you were to compare it to GeoPandas, if you wanted to do a plot on there, you couldn't create bar charts and other information with that. We let pandas do what Panda has to do, and all the spatial stuff that we specialize in, we put it into its own namespace, and we can specialize in that aspect. It can use multiple geometry engines, and it's cross-platform. So if you're on Mac and you don't have access, or Linux and you don't have access to ArcPy, you can leverage Shapely, and it'll pick that up, and you can do geometry operations on Shapely without having to switch and use a different product. It obviously favors ArcPy first, then it'll go to Shapely, and then you don't have a geometry engine as all. You can also read and write information using PyShape. You can use ArcPy, and you can use Fiona. So once again, as you use it across the platform, you can leverage other third-party libraries that are out there for consuming of information and not worry about it. That I don't have ArcPy, can I read this shapefile? Can I read this file geodatabase feature class? Because in the back end, we figure that out and see what you have and see if we can consume it. So let's look at a small demo using spatially enabled data frames. So what I'm doing here is I'm taking information that's not even spatially enabled at all. This is crime data that I found for a city in Georgia, the city of Dunwood, that they hosted out on their open data site for the city. And I'm pulling that in and I'm getting it back as raw JSON. I'm then going to flatten out the data using Panda's normalized JSON function, and I get a data frame. And the first thing you notice is that the column names are kind of funky, and we need to clean it up. And it's still not spatially enabled. So we're going to look at the column names and see what we have. We're then going to use pandas, and we're going to start importing our and adding our namespace to pandas. So we're going to do from ArcGIS.features import GeoAccessor and GeoSeries accessor. Oh, it is? Yeah, hold on a second. When technology fails. Nope. Here, let me try switching over to Youngyo. Just take this out, yeah. About 5. Yeah. Still doing it. Okay. Is that any better? No. I think we're just gonna, I apologize, I think we're gonna have to just grind through it. So give a second, I'm gonna import some scikit-learn libraries here. And what I'm gonna do is I'm gonna use method chaining, and I'm gonna create my data, and I'm gonna sort of clean it up in all one felt swoop. So we have our pandas data frame, we're gonna load it in, the crime data, and the first thing we're gonna do is we're gonna rename our columns. So the rename function is going to go over and it's going to rename the ones with the special characters that we want to replace, and it's just going to make them easier to understand. Then we're going to use lambda functions to convert our string datetimes to datetimes, and then we're going to assign types all in one swoop. And what this does is now we don't have to make multiple passes over our data set. We can do it all in one felt swoop and in one function call. So this data set, as we look at it, isn't very large. But if we had millions of records, you would have a real problem, because it would take a long time. So each pass would consume the same amount of time as you go over it. We can then go through and look at some incident type information. So we're going to use the value counts method on the incident types, because that's what we're interested in. And what you notice is that some of the data has misspellings in it. And because pandas is a mutable object, we can go in and fix that. So we can use the query syntax, pass that in using the lock location, and update that to thefts. And we see that we've fixed the category that we had, and we change it to what we wanted. We can then go ahead and geo-enable our data frame. So we do pd.dataframe.spatial, because we're doing that data set operation. And we're going to do from XY. So we're going to pass in our DF, give it a spatial reference, and the XY coordinates. Now we have a spatially enabled data frame. So that means we have a geometry column, and it's stored in there with spatial information. We can then go ahead and visualize our data set. Or not. Also lost internet, so I apologize. And we can leverage the group by functions to start doing to start translating the number of instances that we have at a location and transform it. We can plot them back on the map. I'm also going to leverage the DB scan that's part of it to do clustering analysis on there using scikit-learn. So we're going to create our model. Oops, sorry. Now I'm flailing. We fit the model and apply the labels back to my spatially enabled data frame. Then I'm going to use group by to get the counts based on each label to find the intensity of crimes that I was interested in, and put that back into a new spatially enabled data frame. So instead of doing an aggregate that you can do using geoprocessing, if you have latitude and longitude that all apply to the same location, and a lot of crime data is pointed back to actually address neighborhood, you can just group by both latitude and longitude, or X and Y, and then do value count aggregations on it, and to save some credits or to do the analysis. So you can do it all locally. Then we get the results back out with our counts, and we can leverage interpolation to create a continuous service for the number of crimes in that area and display it on a map. We can leverage the SDF final spatial plot and use the advanced rendering engine that's available and display the stuff as natural breaks. And if we had a map, we could also display the legend to actually show how it is. So we're going to go back to our presentation. So now we're going to talk about data science with ArcGIS and the data that you can access it. One thing that the ArcGIS platform provides is living atlas information. And it provides multispectral, temporal, and dynamic image layers. And also all kinds of demographics and boundary information and Earth operations in urban systems. Your data and your org data can be shared, so you don't have to just take the information that you have and keep it to yourself. You can develop an open community, you can leverage open data itself, and all be put on a community so you can share information. Personally, I feel that data isn't meant to be hoarded, it should be shared. I'm a big believer in open data, and that information should be shared publicly, especially if it can help other people. The platform also has rich visualization, and you saw a lot of that today using the web maps to do that. But you can integrate with third-party libraries. You can use things like Seaborn, maptplolib, Plotly, those libraries to take how you want to look at the information and make it look even better, to fit the needs for your organization or derive the informational products that you need at that moment in time. Python allows you to do that. You've seen a lot of analysis that you can do. Well, you can also leverage geoprocessing tools through your WebGIS, and we saw some of those tools earlier. But you can create custom geoprocessing tools and host them on your individual servers and put that out there for either other individuals to use or for you to use across your organization. We have Geo Analytics, which is for large tabular and vector data, and we can also leverage imagery and raster analysis. There's libraries to handle your data wrangling, and we solve some of that with pandas. You can also use NumPy, SciPy. And then we have machine learning libraries where you can use scikit-learn, TensorFlows, FastAI, PyTorch, and that's a lot of the stuff that the ArcGIS Learn module is there. So you can start building out more models. You can do very specific geospatial analytics like PySal, which is a great open source library. You have GDAL and Shapely and Fiona. For image processing, you can leverage PIL and OpenCV and scikit-image. And you can really you can take our API, extend it out, and build the tools you need to get the answers that you want. So this sort of brings to the question of why Python. And I touched on the popularity, but it solves something called the two-language problem that I want to discuss. And the two-language problem, especially for statisticians, is sometimes you have to do work in R and then you have to go over and do it in another language to get your answer. Well, Python is so wide and has a large reach across the whole platform that you can do it all in Python. So why change and why have to re-import your data again when you can do it in just one language? And lastly is that we can take the information that we're developing, whether it's a notebook or a hosted feature service layer, and reshare it back out. We can deploy it to dashboards, or we can use the Jupyter notebook. You can even push it up to Plotly, and you can deploy other web tools to get your information shared and reproducible workflows, because we're talking about doing science. So what you do, it should be reproducible. So we're going to open it up to some questions. And we're going to take it from there. Rohit, would you like to come up? Yeah. Do we have interoperability with DAS? We don't have. You could use Dask. Dask accepts a pandas data frame, and you could push that to Dask and do analysis that way. Now, you would have to have the library. So if you're going to use multi-machines, you have to have the same setup on every machine as you go across. Obviously, it's just with any distributed network. But yeah, you could get it working. Any other questions? Oh, thank you, sir. Well, so maps can be persisted locally. There's a save function on the map object. So you can get all your layers that you want in that visualization, and you can render it the way you want to render it, and then save that and persist it. So if you're interested in only saving results and sharing it with your colleagues or somebody else or the outside world, you can just save that map and persist it up. And yeah.
Yeah, you can save maps and it becomes an item in your WebGIS. Yeah. If I may repeat the question, it's that do you have a module to work with Geo Event? No, we are working on that module, so it's not there yet. It's in the roadmap. Yeah.
Yes, sir. Sure. The question is why do we decide to build something else when there's GeoPandas out there? Just to summarize for everybody. So GeoPandas uses an inheritance model that overrode a lot of the existing functionality of pandas, and it was a little one of the things that hurt individuals is when it came to visualization of data. So let's say you wanted to create charting of that. You couldn't do that with GeoPandas. Additionally, GeoPandas also had other issues when it came to dealing with other core functionality, like data types and stuff like that. There was no way to easily identify a geographic column. It had some other issues. It's a solid product, but it just didn't, it also had a lot of holes. So we decided to go with the namespace pattern because one, it was recommended by the pandas team. They said that this is the way you should extend pandas. And two, when it comes to pandas development, I'm not the person to say that I can do this better than pandas, but I can say that I can do geography better than probably the pandas team. So building the namespaces out, we were able to focus on what we do best and let that team, the pandas team, do what pandas does best.
And it also let us interoperate with the ArcGIS platform better. So working with shape files and file geodatabases, reading and writing to them, writing to our map widget. So we get a lot more control and we do a better integration.
Yeah. Thank you for filling that in. Yes. Yes. I mean, unless there's something specific that GeoPandas does that we don't know. I don't know every function in and out of GeoPandas, but in general, yes, I would say. Any other questions? All right. I guess we're done. Well, thank you.
All right. Thank you.